Yeah, thank you. Thank you to the organizers for the opportunity to give a talk here and to be in the Ruhr Universität. So I'll be discussing some joint work with Florent Avier. It's part of a kind of ongoing and broader project, which is studying Stanley's Young Fibonacci lattice. So this is some very close relative to the lattice of integer partitions. For example, the Young Fibonacci lattice, which I call YF, it governs the representation theory of a tower of semi-simple algebras. So these algebras are some sort of counterpart to the symmetric groups. It also supports a version of the Robinson-Shenstedt correspondence. And this RS correspondence sort of reflects intimately in the structure theory of these algebras, which are called Okada algebras. So let me first just tell you what this Young Fibonacci lattice is. We'll do it in the language of Fibonacci sets. So a Fibonacci set of rank n is a subset it's a subset of 1 through n whose cardinality has the same parity as n. And if we order the elements of S in increasing order, then the lth element has the same parity as its index. Okay. We have to be a little bit careful because, for example, the set 1 to 5 is a Fibonacci set both of rank 5 and rank 7. So to indicate this dependence, we put a subscript. So it's a set plus this rank data. And a little bit of thought reveals that the number of Fibonacci sets of rank n is exactly the nth Fibonacci number. Okay? And so in this language, the Young Fibonacci lattice, as a set, it's just all Fibonacci sets of all ranks. It's ranked, so at rank level n, you see all of the Fibonacci sets of rank n. And the covering relations of this poset, or if you like, the edges in this Hasse diagram, are given by the following prescription. There's a covering relation from S to T. If you can get S by either taking T and removing its maximal element, or vice versa. And so, what are some properties? It's ranked clearly. It's actually also a lattice. And it's also one differential in Stanley's sense. And let me just briefly tell you about this differential property. So whenever I have just any locally finite poset, I can define what are called up and down operators on the vector space spanned by the elements of the poset. And in the differential case, you require that these up and down operators satisfy this Heisenberg commutivity relation. Okay. In addition, it should be ranked, and there should be a minimal element. Okay. So the important observation that Stanley saw in his paper on differential posets is if we let W be an element of a differential poset, and dim W denote the number of saturated chains. So these are paths in the Hasse diagram going to W. And if we take the sum of the squares of elements which all live at rank level n, then they tally to n factorial. And this is indicative of the possibility that there could be a Robinson-Shenstedt correspondence. In other words, by that I mean a bijection between pairs of saturated chains ending you had a common point and permutations. So just to be clear, by saturated chain, that's what I mean. Just a path starting at the bottom and going up to whatever element we're interested in. So just some history. So Stanley had this notion of differential posets, I guess, in 1988. And of course, the main example of a differential poset is the Young lattice. And the Young Fibonacci lattice was set up as a kind of alternative, interesting example. Soon after, Sergei-Fomin showed that these differential posets indeed have a Robinson-Shenstedt correspondence. And in keeping with that, there were a series of authors who studied accompanying or attending theories of tableau for this RS correspondence. So Robbie in 1991, Kilpatrick, and then Neusechup in 2009 all studied variations of tableau. And then in 1994, Okada showed that actually there is a family of algebras whose Bertelli diagram is the young Fibonacci algebra. And these algebras we call the Okada algebras. And so today, basically, I want to give a kind of a diagrammatic understanding of these algebras. These algebras are, I guess, now 30 years old, but we would like to have some visualization of them, and also a diagrammatic understanding of this RS correspondence. So, okay, here is what the Okada algebra is. We work over some field, which for the moment we can take to be the complex numbers. The algebra will depend on parameters, so capital X and capital Y are two sequences of parameters taken from this field. And the Okada algebra, ON-XY, so it's generated, it has n-1 generators, EI through En-1, satisfying this kind of Coxeter-style representation. The E's are quasi-idempotents. They square to themselves with involving one of the X parameters. They commute when the indices are far enough apart, and otherwise they satisfy this triple relation when they're neighboring. This is somewhat reminiscent of a temporally Lieb relation, and indeed, if you specialize the x's and y's in the right way, you can get the temporally Lieb algebra and also the Blob, the Martin-Salyer Blob algebra as quotients of this Okada algebra. So sort of some good follows from this. Some known examples other than itself could follow from this. Yes. So Okada showed in his paper, 1994 paper, that when these parameters are generic in the appropriate sense, this algebra is semi-simple and has dimension and factorial. There is a bijection between the Fibonacci sets of rank n and isoclasses of irreducible representations of these algebras of ON. And the dimension, if S is a Fibonacci set and VS is the corresponding irreducible representation, then the dimension of VS is exactly this saturated chain counting, okay? It's the number of saturated chains from the bottom up to S. Like in the Young lattice, the YF lattice governs how these representations branch. So if I take a representation, VS of the nth Okada algebra and I restrict it to the n-1st Okada algebra, well, of course, it will break up. And the components, the irreducible representations which contribute to that restriction are exactly governed by the covering relations. And finally, I mean, this is important, but not for this particular talk. He defined a theory of symmetric functions here, called clone functions. There are Koska numbers, there's an induction product, and indeed there's even a clone Littlewood-Richardson rule. But we won't go into that. So to make things work here, I want to talk about visualization. So we want to visualize elements of this algebra. In particular, we want to visualize, say, monomials. And so to do that, we use this artifice of a diamond grid of height n-1. So here n would be 6. And I just fill it randomly with black tiles, okay? And whenever I have such a filling with black tiles, I can, if I read this kind of from left to right and top to bottom, I can obtain a monomial in the Okada algebra. And vice versa, if I have a monomial in the Okada algebra, I can parse it kind of in a certain canonical way so that it's realized as such a filling. And then once we kind of working in this combinatorics of diamond graphs, we can do a sort of standard trick, which is to replace black and white diamonds by these non-crossing art fragments, which are either vertical or horizontal. And if we stitch these all together, we get a collection of non-crossing arcs and possibly loops, which is commonly called a fully packed loop configuration. And in the language of loop configurations, these Okada relations are just implemented by these local moves. So, for example, the idempotency quasi-idempotency relation just corresponds, for example, to the removal of loops. So when we have such a fully packed loop configuration and an arc in it, for example, we can look, if this arc will, of course, descend to some bottom level, and the position of that bottom level we call the height. So here, in this, we have an arc that goes from 5 to 3, and it actually comes to the basement, so we declare that it has height 1, right? Whereas this arc here goes from 5 to 4, and somehow dips down to level 2, so we say it has height 2. And these local moves 1 through 3, will never allow us to extricate an arc from its basement level. And so this means that the height is an invariant of the local transformations. So what we'll do is, such a fully packed loop configuration is kind of too much information, so we want to abbreviate it. And in particular, we would like to just record the connectivity of the diagram, its non-crossing properties, and also this height information, because the heights are invariant, as I said. And we encode that in what we called an Okada arc diagram. This is basically a temporally Lieb diagram where the arcs have been labeled by their heights coming from the fully packed loop configuration. Right, so this is just a prescription for making this Okada diagram. So this, in particular, the thing on the right is an isotopy class of arcs where we've thrown out any loop. And not every labeled temporally Lieb diagram is going to come up this way. There's some constraints on these labels. So for example, it's clear the height has to be bounded by the min of the endpoints. Like, for example, if we look at the green arc going from 5 to 3, its height can never exceed 3, obviously. Actually, in this case, it's 1, but so we have a bound on the heights of an arc. A little bit of thought reveals that the height actually has to have the same parity as the min of its endpoints. And then finally, these arcs, they can nest one another. So for example, the blue arc here joining 4 and 5 is kind of nested, above the arc joining 3 and 5. And so clearly, just from that topological consideration, the height of the blue curve has to be strictly larger than the green arc. So the heights are increasing with respect to this nesting order. And from the point of view of the Okada arc diagram, this can be seen in the following way. We can take this diagram and take the, if you like, the rooted forest dual to it, and the prescription is that the height labels should increase as we move away from the roots. The roots in this case are all of the arcs labeled 1, right? So you can see as you move forward on one of these red arrows, you increase. So that's an Okada arc diagram. Here's a formal definition, but maybe I more or less told you this. Here are examples. The one on the left is very regular. Everything is just moving horizontally. We can always make that in any Okada arc diagram, and it will play the role of some kind of identity. On the right is some more exotic thing. I've indicated the associated forest, and you can see, just by inspection, you can see that the height labels are increasing as you move away from the roots. Okay, and now, of course, like in the temporally Lieb algebra, we want to put these things together. We want to multiply them or compose them. And so if you like, we're going to merge the right-hand side of the left diagram with the left side of the right diagram, right? And when we do that, we get, non-crossing arcs, but also possibly loops. And what we're going to do is, for a given arc, we'll follow it, read it from left to right, and we'll take the minimum of the H labels we encounter along the way. And that minimum will be the new H label of the corresponding arc on the right-hand side. So this arc joining 5 and 7 gets sort of isotoped into this with label 1. And loops we remove, but we remember that there was a loop by putting an x parameter, and the index of that x parameter should be the minimum of the height labels. Yeah. And okay, as you might hope, the composition, up to the scalar that comes from the possible creation of loops, the composition of two of these diagrams, of two Okada arc diagrams, is again an Okada arc diagram. And so we can make an algebra. So we take the vector space spanned by all rank n Okada arc diagrams, and it becomes an associative algebra under this composition with unit that parallel object diagram I wrote.
Sorry, is it clear that there's only one monomial when you compose? In your example?
So I haven't given a prescription from writing the monomial from the temporal Lieb diagram.
In your previous example, you had an x1, right? Because there was one loop.
Yes.
So in principle, there could be a product of monomials?
Oh, yes. Oh, yes. I'm sorry. Yes. Monomial of the x's. Yes, there could be many loops, and for each you have an x. Yeah. Yeah, I should also mention that actually implicitly here I'm assuming the y's are all 1, but the full formula involves y's actually. But and finally, our main result, if you like, is that of course this Okada arc, the Okada algebra is isomorphic to this arc algebra, and the isomorphism is implemented by sending the Okada generator Ek to this element script Ek, where script Ek is essentially a temporal Lieb generator of the temporal Lieb diagram, which has been appropriately labeled. Okay, and we have n-1 of these arc generators. Okay, here's the formal definition on the left. Yeah. And just some comments on the proof. It's not hard to check that these arc generators, these arc elements, that they satisfy the defining relations of the Okada algebra. So this means our map is well defined. They also generate the arc algebra, so everybody factorizes in terms of these. And so the map phi is onto. And the target of this map, namely the arc algebra, has dimension n factorial. So phi is an isomorphism. Other way said, the number of... it's curly EI is this picture here on the left. So it's a temporal Lieb generator where all of the horizontal strands get an H label of their height, and then you just have a special prescription for these two caps. Yeah. Yes. Okay. So said differently, the number of Okada arc diagrams of rank n is n factorial. And the proof of this is essentially a diagram version of the RS correspondence in this case. And if you don't mind, with the last amount of time, I'll explain that bijection, this fact with an example. So just some preliminaries. If I have an Okada arc diagram, then we say an arc is propagating if it just joins the left and right of the diagram. And P lab, it means propagating labeling set of the diagram, is by definition the set of all of the H labels of the propagating arcs. And it's an important observation that this set, P lab, is a rank n Fibonacci set. So this immediately bridges us to the world of the Young Fibonacci lattice. And so the idea is to make a bijection. So given a fixed Fibonacci set of rank n, we want to make a bijection between the rank n Okada arc diagrams where this propagating labeling set is S, and pairs of saturated chains in the YF lattice which share S as a common endpoint. Okay, and this, let me just do with an example. So here's an Okada arc diagram whose propagating set in this case is 1, 2. And I'm going to build two saturated chains. I'll situate them on the left and the right of this diagram, and here they are. So they're chains, you can check. They both end at the Fibonacci set 1, 2 of rank n, as they should. And so so let me just tell you how these are built. So for example, in this space between 5 and 6, we'll sit the fifth element of the left chain. So how do I get this Fibonacci set? I draw a curve going south, sort of minimally crossing the arc diagram. And then I record the arcs that are crossed and the labels of those arcs, in this case 1, 2, 3. And so the Fibonacci set sitting at position 5 will be exactly 1, 2, 3 of rank 5. Okay, and then we repeat that for each interval here, and we get the left chain, if you like, and then we do it on the right side, and we get the second chain. So let me say a few things to end. With this, we can do a lot now with this diagrammatic way of seeing the Okada algebra. So for example, having this diagrammatic setup allows us to revision or reinterpret, give a different model for the irreducible representations of the Okada algebra. So the so-called cellular description of the representations. So for example, given a Fibonacci set S, I want to look at, say, the irreducible representation Vs, and we can realize it as the span of what are called of half diagrams. So Okada half diagrams. These are just basically taking an Okada arc diagram and just cutting it in half. Here, I've just done an example of rank 5, where S is 1 sub 5. There are 8 half diagrams in this case, corresponding to the 8 saturated chains that travel up to this point in the Young Fibonacci lattice. And the action of the algebra is, of course, the diagrammatic action. I take an element of the Okada algebra, which I think of as a diagram, and I just multiply on the left against the half diagram, and the result is another half diagram. It's either 0 or another half diagram. If the half diagram has a propagating set which is still S, that's what it is. If the propagating set changes, then it's set to 0. And what's indicated with all of this busy system of arrows is the action of the various generators. Okay, so this is a kind of picture of the module. And you'll notice that there are sort of 3 shaded regions, 3 rectangles here. These correspond to the irreducible representations that show up when I restrict this representation of rank 5 down to rank 4. Okay, so when I restrict to the Okada algebra of rank 4, it becomes reducible, and it has 3 components, 2 of dimension 3 and 1 of dimension 2. And all of this is just immediately can be seen just on the diagrammatic level. So that's some fruit that can be, some benefit that flows from this. I mean, there are many other things. Right now, we're working on using this diagrammatic setup, using it to, for example, find a semi-normal basis for the Okada algebra, and also trying to solve an outstanding problem, which is kind of where I started from, is to find the Jussy-Murphy elements for the Okada algebra. And I think this will afford us a venue to do that, an approach to it. So I think I'll end. Riesen Dank, and to the mathematical prospectors, Julie Kauf.
All right, thank you very much. Are there any questions? Oh, there are plenty.
So if you set all of your parameters to 0, I imagine this is a non-semi-simple case.
Yes, yes.
And do you know about the irreducible representations for this?
No, no, we haven't really investigated the non-semi-simple case. I mean, in fact, if the first thing to do is just to consider the case when all of the parameters are equal to 1, which is the monoid case. And that's actually already non-semi-simple. So I think Florent and I were just discussing this last week. I think maybe we can make some progress there, but like, that's a whole world to investigate, definitely.
Thank you.
Yes.
Can I ask a question? So do you have a way to compute the characters of these irreducible representations?
So there is a character theory that actually Okada had in his paper. I mean, when you're talking, I don't know, from my understanding, when you're talking about algebras, characters or character tables is a bit nebulous since we don't really have conjugacy classes. But there is a character table. Functionally it plays the transition between. I mean, I haven't talked about this, but there are some kind of Schur functions here, and some kind of power symmetric functions, and it translates between them. Oh yes, yes. There is an analog of that recursion. Yeah.
Okay. Thanks for the talk.
Yes.
I have a question. So when I think of Sn, I think of Sn acting on tensor powers of standard representation of GLM.
Yes.
And is there something like this here? And like, what's the Schur-Weil dual?
There's no obvious Schur-Weil duality here. I mean, except for low rank. So in low rank, so for n which is 1 through 4, there's a happy coincidence that the Okada algebras are isomorphic to the group algebras of the symmetric groups. So there's Schur-Weil duality there. There is also, strangely, Schur-Weil duality at level 5. So you can write the Okada algebra as an intertwining algebra for GLV at level 5. But after that, we don't know. So, but this is one of the things we want to get is we want to understand Schur-Weil duality here. Yes.
Well, thank you for a great talk. So you have these beautiful combinatorial models for the irreps of the Okada algebra. So for the symmetric group algebras, you have these actions on Tableau, promotion, evacuation, which for the KL basis, Kacshan-Lustig basis, can be modeled by the action of, say, the long element or the long cycle in Sn. Are there combinatorial symmetries of these half-arc diagrams that have actions that can be modeled by Okada algebra elements?
Say the last sentence.
So do these Okada, these half diagrams, it's my first time seeing them, but do they have some interesting combinatorial symmetries in that set that can be reflected by elements of the Okada algebra acting on corresponding bases of the irreps?
I'm not really sure how to answer your question. I'm not sure what. I mean, there's no Kacshan-Lustig theory here yet. I mean, maybe there's some kind of analog, but can you give an
So for example, for the temporally Lieb algebra, right? You can sort of think about non-crossing perfect matchings,
Yes.
right? These are indexing irreps of the symmetric group. And you can think about a Kacshan-Lustig basis, but there are other models for getting that particular Kacshan-Lustig basis. It's very nice, this Catalan dimensional thing. And the action of the long cycle in the symmetric group will correspond to rotation up to sine.
Okay, so you're saying that the temporal Lieb story somehow reflects in the Kacshan-Lustig theory of the symmetric group?
Yeah, that's right.
And you're asking whether or not this says something about the symmetric group in some way?
Or I guess what I'm saying is that you have a very nice combinatorial model for these bases. So if I'm thinking of these as playing the role of like Young Tableau or something.
Sorry, one question. Is it true that the Kacshan-Lustig basis of the symmetric group is the same as the cellular basis?
So the Kacshan-Lustig basis of the symmetric group induces the cellular basis on the irreps. That's how I would put it.
Because this is the cellular basis.
It's A, not the. There's many cellular bases.
Sure.
Oh, yeah.
Okay. Maybe we, okay.
We'll talk later, I'm sorry.
Is there an interpolation, some sort of algebra that interpolates between the group algebra of the symmetric group and these Okada algebras? All of which would have, is there some sort of interpolation between the group algebra of symmetric groups and
No, I don't.
all of which would have dimension and factorial? I'm just thinking of the fact that you can, like, for example, start with Young's lattice and then maybe do some sort of moves and still get the differential poset.
Okay, I don't believe so. I mean, you could ask the same question for the Wald-Brouwer algebra. It also, one of the Wald-Brouwer algebras also has dimension and factorial. I don't see a connection in general. I mean, outside of these incidental isomorphisms of low rank, right? I mean, one thing one can do is one can kind of play the two RS correspondences off one another, right? You can, go from the RS correspondence in the Young lattice and then push it through into the, and they can play that kind of game, but I'm not sure if that's going to do what you. Yeah.
Another thing you can do is to mix permutation and those diagrams together. So those kind of label permutation, and you would get a label Brouwer algebra or something like that. But maybe that's not your question.
That was kind of it.
Yeah.
All right. There's 2 more questions.
Okay.
Do you have a guess of what might be RSK?
Well, there is already a candidate for RSK. So Florent's student, Geneviève Neuserchap, basically set it up. It's very easy to calculate. It has some strange, I don't want to say defects, but I mean, so it takes a sequence and it produces a pair of standard and semi-standard tableau here, but not every. So it's an injection. Not everything is realized. So not every pair of standard and semi-standard tableau is realized. So, which is again a kind of indication that something is funny with Schur-Weyl duality if it exists, right? So, but yeah, there is a candidate at least for that. Yeah.
Okay, maybe we take the other questions offline.
Yes.
Thanks again.
Thank you.